Okay, welcome to Unit 17, Quantified Logic in the English Language. Tonight we're going to be talking about how to translate some typical forms of quantified sentences into QL. So last time, remember, we were introduced to the universal and the existential quantifier. And today we're going to look at how some of these quantifiers are used in some common logical sentences. So you may have looked at this activity on your Unit 16 handout. This handout asks you to consider the following kinds of sentences. It says, historically, many important claims in philosophy are about how different categories of things relate to one another. For example, how things that are doctors relate to things that are smart. So this is just one example. This isn't typically a philosophical example, but it's an easy one. So we might say all doctors are smart, no doctors are smart, some doctor is smart, and some doctor is not smart. So these are considered to be classic forms of sentences that are related to one another in some important ways. In fact, these were studied by the Greek philosopher Aristotle, and so they're known as the Aristotelian forms. And Aristotle's logic in particular is known as a categorical logic because it relates categories of things, A's and B's. So it relates those to one another. So in effect, what these sentences are saying, all doctors are smart, no doctors are smart, some doctor is smart, and some doctor is not smart, are the following. All A's are B's is the form of the first sentence. No A's are B's is the form of the second sentence. Some A's are B's is the form of the third, and some A's are not B's is the form of the fourth. In fact, Aristotle indicated these four sentences using vowels. So the first set of sentences have been traditionally called A sentences, all S's are P's. The second form of sentences have been called E sentences, so no S's or P's. And the third form has been called a I proposition. And then the last one is what's called an O proposition. It'll be important why we have these labels in a moment. But how do we signify each of these things? Well, the fact is, if we want to say all doctors are smart, what we need to say is that for all things X, if X is a doctor, then X is smart. For the second form of the sentence, no doctors are smart. One way in which we might express this is by saying, for all things X, if X is a doctor, then it is not the case that X is smart. Or we might also say, there does not exist something X such that X is a doctor and X is smart. So that'd be another way to express that idea. Some A's are B. So what we'd say there, we'd say there exists something X such that so some doctor is smart here. There exists something X such that X is a doctor and X is smart. And then for our last one, some doctor is not smart. We would say there exists something X such that X is a doctor and it is not the case that X is smart. So these are our Aristotelian forms. The way in which these relate to one another is the following. So if we have a sentence of the A form, again, all A's are B's. A sentence of the E form, no A's are B's. A sentence of the I form, some A's are B's. And a sentence of the O form, some A's are not B's. Then these sentences bear some important relations to one another. So the first thing to notice is that the sentences that lie on opposite corners from one another are contradictory. Okay? So they're contradictory, and what does that mean? That means the truth of one implies the falsity of the other. So these guys are contradictory with one another. These are contradictory with one another. Okay? So for example, if we know that all A's are B's, then we know that it's false that some A's are not B's, right? And similarly, if some A's are not B's, that implies the falsity of all A's are B's, okay? Going the other direction, we get the same kind of thing, right? Some A's are B's implies the falsity of no A's are B's, okay? So those sentences contradict one another. If one of them is true, it implies the falsity of the other. The other can't be true. These sentences across the top, the A and E, try to put that a little higher. These are what is called contrary. So these two sentences are contrary, and what that means is that they can't both be true, right? So it can't be true that all A's are B's and that no A's are B's, right? Those cannot both be true at the same time. The bottom two here are what is called subcontrary. And so what that means is that they cannot both be false at the same time. So all A's are B's and some A's are not B's cannot both be false, right? If all A's are B's is false, then it has to be true that some A's are not B's, and vice versa. If some A's are not B's is false, then it has to be true that all A's are B's, okay? The sentences on the side here have a different kind of relation to one another. So what we want to say about these guys is that they have they are what is called these are what is called subalternations of one another, or they're subalternations. So they involve the subalternation relationship. So this sentence A, if it is true, then it implies, so if we have A, all A's are B's, and then I, some A's are B's, that implies the truth of I. So A implies the truth of I. E implies the truth of O. No A's or B's implies that some A's are not B's. But the relationship doesn't go the other way, right? If we know that some A's are not B's, that does not mean that all A's are B's, right? So these bear that truth relationship to one another. I alert you to this because later on when we're constructing proofs, it may be useful to revisit this because these logical relationships can be helpful in thinking through the way in which you can derive one sentence from another. But the main thing to take away is that these are our Aristotelian forms and that those are going to be important to the way we translate a number of arguments. Okay, so let's turn back to the PowerPoint now. So we have here our forms that we talked about previously. These are those forms that I just introduced you to, the Aristotelian forms. We're now going to look at these in a little bit more detail. So consider this example. This example comes from your textbook on page 141. So here's the example. Every coin in my pocket is a loonie. This is an all statement, so it's going to use our form all P's are Q's, which we might symbolize again like this. So how are we going to symbolize this for this specific example? Every coin in my pocket is a loonie. Well, we might first of all consider our universe of discourse to include all coins. And then we might have a few different predicates in this language. So we might have PX, which means X is in my pocket. We might have TX, which means X is on the table, or LX, which means X is a loonie, or DX, which means X is a dime. But the way we're ultimately going to end up representing this sentence is in this way. So this is the translation of this sentence. Every coin in my pocket is a loonie. And so what this says is, for all things X, if X is in my pocket, then X is a loonie, okay? So that's how you're going to translate an all S's are P sentence like this, every coin in my pocket is a loonie. Now notice, you might have thought that something like this is the correct way to translate that sentence. So maybe you thought that the way we should translate this is for all x, px, and lx. But in fact, this is incorrect. So what does this actually mean? All x, for all x, if they're, for all x, they are px and lx. Well, what this means is all, whoops, upside down A, all, and we're just going to say coins because that's what our universe of discourse is, the universe of coins. All coins are in my pocket and loonies. Okay, so that means something quite different than all the coins in my pocket are loonies, or every coin in my pocket is a loonie. That says, in effect, that all coins, and our domain of discourse includes all coins, so all of the coins in existence are in my pocket. Lucky me. Unfortunately, they're all loonies too, so I can't spin them around here, but that's okay. I can trade them in and be a millionaire in Canada. So this is, but this is not going to capture the same sense that we were looking for. So you do not want to use this one to translate your all S's or P's sentences. Instead, use this guy for all X's. If X is P, then X is L. Okay, moving right along. Let's look at some and some not sentences. So remember, if we want to symbolize a sentence of the form some P's or Q's in the following way. There exists some X such that X is P and X is Q. So an example might be, some coin on the table is a dime. And so recall, we have a dime predicate here, and we have a table predicate. So we might symbolize this as follows. There exists some X such that X is on the table, and X is a dime, right? So that would say some coin on the table is a dime, and that is what we're looking for there. So this is the correct form of translation for some coin on the table is a dime, or in general, for some P is Q, okay? If we want to say some P's are not Q's, if we want to express the O sentence, all we need to do is throw that negation in to that last predicate statement. So this would say, you know, there is some X such that X is P, and it's not the case that X is Q. If we wanted to have a sentence here, we wanted to say, for example, there aren't any, we wanted to say some of the coins on the table are not dimes, right? The way we would say that is, there exists some X such that X is on the table, and it is not the case that X is a dime. Okay, that's how we would express that guy. All right, so that's some and some not. Let's move ahead. First, actually, let's look at a few translations. So some more activities here. So some X, TX, and DX is the correct translation of some coin on the table is a dime. The following sentence is not a correct translation for this. What this says is, so this sentence says, there is something X such that if X were on the table, it would be a dime, right? So this might be true for a dime that's in my pocket, for example. So suppose there are no coins on the table, but I have a dime in my pocket. Well, then it is true that there exists some X, the coin in my pocket, such that if it were on the table, then it would be a dime, right? That coin is a dime, so if it were on the table, it would be a dime. But it is not true in this case that there is some coin on the table that is a dime. So this is the preferable translation for this sentence, for the some sentence, okay? So just be sure not to get tripped on that. With the some sentences, we're going to use conjunction as opposed to conditional. All right, moving ahead. How do we express statements about the non-existence of things? How do we say, for example, that none of the coins in my pocket are dimes? Well, what this would look like is the following. So if we have a statement, no P's or Q's, an E statement, it's going to look like this. For all things x, if px, then not qx, okay? So if we want to say none of the coins in my pocket are dimes, the way that we would say that is for all things x, if x is in my pocket, then it's not the case that x is a dime. Now note, this can also be translated as it's not the case that there exists something x such that x is in my pocket and x is a dime. So there's not something that's in my pocket and a dime, right? And so if we want to translate it that way, we would do this. It's not the case there exists some x such that x is in my pocket and x is a dime, okay? So in effect, that says it's not the case there's something that's in my pocket and a dime. This one does. The first one says, for all things, that everything in my pocket is a non-dime in effect, which is a little bit strange, but I find it more natural actually to translate these sentences into the top form than the bottom form, but you may find the bottom form more useful, and indeed one of them may be more helpful as you're constructing an argument. But the important thing to take away from this is that you can use the existential quantifier to translate none sentences, but that will influence the connective that you use. So if you use the existential quantifier, you will be using, again, a conjunction symbol. If you use the universal quantifier, you will be using a conditional. Okay, moving right along. So let's think about this. What is a contradictory sentence for all x, px, then lx? So what's something that contradicts for all x, px, then lx? We might want to put some meat on the bones of this sentence, as it were, to think about this. So what would contradict the sentence, all the coins in my pocket are loonies? Well, it would contradict this to say none of the coins in my pocket are loonies. So maybe we would want to say that this is a contradictory sentence. It's not the case that there exists something x such that x is p and x is l. And so that is contradictory, right, for this one. So these two guys do not go together. What about this one? What's a contradictory sentence for all x? If x is p, then it's not the case that x is q. Well, the answer here, as we know, since this is equivalent to this thing, is the following. For all things x, px, then qx. Right? The top one says it's that everything in my pocket is not a loony. Nothing in my pocket is a loony. And the second one says everything in my pocket is a loony. And so those two things are contradictory. And here what we've got, again, is the Aristotelian square of opposition at play. So in getting this, all x, px, then lx, to not ex, px, and lx, where we're moving from is from A to O. And in moving from, and then obviously it's the same in the other direction. So that's the way those, we can generate contradictory sentences using our quantifiers. And again, those will be helpful for you as you go into working proofs with quantifiers, which we'll be moving on to very soon. So a word now about empty predicates. Predicates in our language in QL can be empty, which means that they don't describe any object in the universe of discourse. However, just because a predicate is empty, just because it doesn't actually describe anything in the universe of discourse, right? I mean, let me give you an example of this first, right? So, so think about the language we were using previously, which had the predicate dimes, the predicate, and the predicate, well, it had the predicate x is a dime, and it also had the predicate x is a loony. Well, suppose that our universe of discourse applied not to all coins, but only to Canadian coins. Well, in that case, the X is a dime predicate would be empty. It doesn't describe anything in our universe of discourse. Now, just because a predicate is empty, it doesn't mean that there aren't truths that involve it. So consider this predicate is a unicorn. And now suppose our domain of discourse is all animals on the planet Earth. And we have these two predicates, UX, which means X is a unicorn, and HX, which means X has one horn. Well then, the following sentence is actually true on our planet, on the planet Earth. It is true that all unicorns are creatures with one horn. I mean, that's built into the definition of what it is to be a unicorn. It is true that all unicorns are creatures with one horn. Anyone who knows the definition of unicorn knows that that's true. But the following is not true. It is not true that there exists some X such that UX and HX. That's false. There is no creature, it's not the case that there's some creature that is a unicorn with one horn, right? So in this world, it's true that all unicorns have one horn. Again, it's part of the definition of unicorns, but that doesn't actually mean some animal is a unicorn. Unicorn is sadly an empty predicate in our world. So you can have truths about objects that are not represented in your world. You can have truths involving empty predicates, but there are also instances where a sentence is going to entail that something has to exist, and if it says that about a empty predicate, then it will end up being false. Okay. I think that there are a number of things to notice now about our universe of discourse. And again, what is our universe of discourse? It's just the stuff that we're talking about when we formulate logical sentences. So first of all, a universe of discourse must have at least one member. So this is an important rule for talking about our universe of discourse. It makes it the case so that some of our logical inferences using our universal predicates and our existential predicate, our universal quantifier and our existential quantifier work. So this is an assumption we just need to make. If something is a universe of discourse, it has to be at least one, about at least one thing. Additionally, a predicate may apply to some, all, or no members of the universe of discourse. So unicorn applies to no member of our actual world. But it's possible to have a predicate that applies to just some members of our world, like is a human being, or to any universe of discourse we're talking about. And it's also possible to have a predicate that applies to all objects in our world. So like has mass might be something that applies to everything in our world. It's a controversial statement, but I think I at least would buy that one. Okay, and then the last thought is that a constant must pick out exactly one member of the universe of discourse, right? So a member of the universe of discourse may be picked out by one constant, many constants, or none at all. But a constant has to pick out exactly one member of the universe of discourse. So we're not going to have names that refer to more than one object in our universe of discourse. Our actual world has names that do. So for example, the name Mark may apply to more than one person, perish the thought, but we are going to make it a rule of our system that a constant picks out exactly one member, a constant or a name, as I've also called it sometimes. And then, but it can be the case that a member of the universe of discourse may be picked out by one constant, many constants, or even none at all, right? So it could be that I am known as Mark and also as Phelan. That is fine within our system. It can be that an object is known as A and also B, but it has to be the case that the name A is picking out one member and only one member of the universe of discourse. Okay. There are important things to bear in mind here about translating pronouns. Pronouns aren't always going to get the same expression in symbolic logic. in quantified logic. The reason is that predicates take their reference from usually some other word that is within the sentence. So consider the following two sentences, right? So here we're talking about people. We're going to say the predicate GX is X can play the guitar. RX is going to be X is a rock star. And then we're going to describe our world as having two people in it. C is Chris and L is Lemmy. Okay, and so what we say is, if Chris can play the guitar, then they are a rock star, right? So this is one of our sentences we're thinking about in the book. And then the other is, if a person can play guitar, then they are a rock star. Okay, now the pronoun they appears in both consequence of these sentences. However, these consequences are not the same, which can be made clear by replacing pronouns. So what does the first sentence look like? If Chris can play the guitar, then they are a rock star. So what that looks like is, if Chris can play the guitar, then Chris is a rock star, okay? The second sentence, however, clearly, because of the first part, for the antecedent of the sentence, is making a statement in general about our world. So what this will be translated as will be using the quantifier. So it'll look like for all X, if X can play the guitar, right? If one of the people in our domain of discourse can play the guitar, then X is a rock star. So the they in the first sentence links back to Chris specifically. And so it gets that specific name in there, right? That specific constant in there with R. But the they in the second sentence refers to no one in particular, but instead to whatever name is substituted in for GX in that world. So whatever individual ends up filling the G predicate is going to be the one that we're talking about when we get all the way over to the consequent in this case. Another important thing to bear in mind, and this will be the last point on today's video, is that when we're dealing with multiple quantifiers, the order of the quantifiers matters. So let's consider some examples here. So first of all, let's talk out with some that do not involve multiple quantifiers. So we have a universe of discourse involving people. We have a predicate, LXY, which stands for X likes Y. And then we have two names, Imre and Carl. Okay, so everyone likes Imre. So what does this look like? For all things X, X likes Imre. Okay, Imre likes everyone. What does this stand for? For all things X, L-I-X. Imre likes X. Imre likes someone. There exists some Y such that Imre likes Y. Someone likes what Imre, right, will be this. There exists some Y such that Y likes Imre. So we can see here from the way these have changed that the order of the variables in the constant here mattered to what this sentence means. But similarly, the order of the quantifiers matters when we're dealing with sentences with multiple quantifiers. So what we have here is, I'm going to skip over Imre likes everyone that Carl likes down to this next one. There is someone who likes everyone will be represented as this. There exists some Y such that for all Y, for all X, Y likes X. So there is someone who likes everyone. Yeah, so this sentence says there's someone who likes everyone, right? What if we had this sentence? For all X, there's some Y such that Y likes X. What this means, so this means there is someone who likes everyone. This means everyone is liked by someone. All right, so changing the order of those constants changed the meaning of that sentence dramatically. Um, looking here, there's someone who likes everyone that likes someone. So what this one says is, there exists someone Z such that for all x's, there exists someone Y such that X likes Y. If X likes Y, then Z likes X. All right? There is someone who likes everyone that likes someone. Right? So this expresses this idea. There is someone, what about this one? There is someone who likes everyone that he likes. How would we translate this? Well, the important thing to bear in mind here is that we can work stepwise to work out these translations. So what we want to do is first, we know this is about there is someone. So it's a there exists something sentence. So what we're going to say is there exists some Z such that everyone who likes everyone that Z likes. So we're going to keep, right, because this is who and he, like all of those are referring to the same individual. So we're going to keep those the same. So we can work through stepwise to try and get this. So we have, so there exists some Z, and then we have all A's. Everyone who likes everyone that Z likes is a B, is liked by Z, right? And so what we translate that to is there exists some Z such that all X's, because we know this everyone here is going to give us all things that Z likes are things X likes, then LZX. And then finally, we just need to translate this last piece, and we would get this complete sentence here, standing in for this long item. So I invite you to have a look at that, to try and translate that yourself, stepwise. And just bear in mind that using stepwise translation is a useful tool in dealing with quantifiers. This will be particularly useful for the homework this week. And I look forward to talking to you all more on Wednesday. So that's it for now. Bye.